This is a research report from TUM, Technische Universität München. All kinds of machines are smarter than they used to be, thanks largely to 20th century advances in microelectronics, software, control, and communications. Researchers in the Munich area are working to redefine smart machines for the 21st century. Along with novel twists on familiar themes, such as the more or less humanoid robot and automated manufacturing tools, they are exploring new ideas that simply can't be fully realized, not just yet. One of these concepts is the cognitive factory, which integrates principles of cognition into every aspect of industrial production, from design through final assembly and quality control, and potentially to the end of a product's life cycle.
We are able to perceive our environment, we are able to enlarge and to enhance our knowledge, and we are able to flexibly react to unforeseen events. And we would like the whole factory to be able to achieve the same capabilities.
Indeed, there is a huge economical long-term benefit that we expect from exploring the possibilities and the potential of cognitive systems in production, and that is to overcome the conflicting goals that we have in production, which are to be flexible on the one side and to be productive on the other side.
In today's manufacturing environments, according to project leader Michael Zeh, a professor in IWB, the university's Institute for Machine Tools and Industrial Management, flexibility comes mainly from people who are far better than machines at learning, adapting to changing conditions, making the most of what they know, and finding creative solutions. Also, people are better at manipulating many kinds of objects and tools. Machines often have the advantage in precision and productivity, especially in mass production environments.
And now the approach is to get a better cooperation between technical systems and humans in order to have both at the same time, to have both in the same production environment.
A demonstration testbed for the cognitive factory has taken shape on the Garching campus of the Technical University of Munich. It's there today to help industrial managers both imagine the factory of the future and take part in its development, and to help researchers break down technical barriers on many fronts at once. A fundamental difference here is a radical reorientation, away from pre-programmed processes and centralized information management. Here, manufacturing is a decentralized process guided primarily by the product itself.
As an enabler for the product-based production control, we're using like the RFID technology, radio frequency identification. So we have got like a quite small chip or transponder, and this transponder consists like of an antenna on the one hand and a small chip where we are able to store the information.
Each RFID tag carries and communicates information about a product's current state, its final state, and requirements that will come into play as it moves through the factory. At some workstations where industrial robots can do what needs to be done, cognitive capabilities can improve their performance and the overall workflow.
And if an error occurs, usually you just get an error message. So when a failure occurs in our system, the system still has a workload which needs to be done. So it chooses from his available workload what can be next steps. So he creates a new solution, finds it, stores it in the database, and has a new solution for his decision making in a later step. So it's improving always and ever.
The key here is not to mimic human cognition or behavior, but to give machines their own ways to get similar results.
We have an abstract model of capabilities, and we have an abstract model of requirements of the product. And this is used to improve the production scheduling.
A similar approach to product design could dovetail with fabrication steps in the cognitive factory.
If we want to create customized products for consumers, which is a growing trend in the market, then we want to be able to first generate them, but then to fabricate them as well. What we want to do is not just simulate alternative solutions, but actually generate them as well.
Another team pushing the limits of cognition in individual workstations, again motivated by a trend from mass production toward the flexibility of what they call mass individualization, is approaching the problem from the angle of data processing research. The techniques they develop may prove applicable to many different types of factory operations, but for now, they're focusing on one of the most difficult ones to control, the use of high-power lasers to cut and weld pieces of metal. The state-of-the-art in laser material processing still requires time-consuming and costly manual trials for setup and quality control.
So we have a cognitive workstation which can learn from a human expert and apply the learned knowledge. The more the machine welds or cuts materials, the better it will be.
Humans can listen, they've got ears, they can touch, they've got fingers, and they have eyes, they can have a look at it. They can even smell with their nose. Our system uses microphones, so it can hear the process. It has photodiodes, so it can see specific colors, and it has video cameras, so it has some really geometric resolution of the process.
This sensory system produces around 100 megabytes of data per second, but the researchers have shown that techniques such as neural networks and so-called support vector machines can enable a 1,000-fold reduction.
Human cognition somehow reduces the reality to characteristics. That's exactly what we do as well. Then human cognition is able to classify, to differentiate those characteristics. We do that as well with classifiers.
Other researchers, including psychologists and ergonomics experts, along with computer scientists and mechanical, electrical, and industrial engineers, are working to optimize computer guidance for manual assembly steps. They also aim to enable industrial robots to be effective and safe partners with people in the workplace.
We are talking about a factory which serves the worker, the human worker, and allows him to be more flexible.
Imagine a worker working on a really complex product. In this complex product, he has his own knowledge about the product and maybe changes the sequence of how he assembles this product. A deterministic guidance system at some point would not be able to help him anymore because he did not follow this deterministic sequence. Our system, in contrast, analyzes the state of the product and from that derives the next feasible instructions to get the worker to the final product state.
Elsewhere on the production line, the researchers envision a master-apprentice relationship between the human worker and the industrial robot.
Of course, during this situation we want to have the workflow between the human and the robots to be as intuitive as it can be. It has to be safe. The problem with industrial robots is that there are no real sensors that can measure if there is a contact with the human being or not. So we have to surveil the workbench. There are no real reliable sensors and perception tools to really understand the human being, what he is doing. And we want to understand by observing the human being what he is thinking about and what he intends to do.
Collaboration has also benefited from a larger research framework created in 2006, a so-called excellence cluster named COTESIS, Cognition for Technical Systems. That in turn is part of a nationwide research initiative funded primarily by the DFG, the German Research Foundation.
What we see here is just one outcome which demonstrates cognitive behavior not only of a single robot, but also of a complete factory.
We need mainly to convince enterprises that this is indeed a promising approach and get them to apply such systems in the sense of a prototypical production environment.
I'm Patrick Regan for TUM Research Report.